Alright, so I'm back and we're going to talk about why we need the complex conjugate when we're converting from S to T, correlation of Y to T, complex conjugate of negative T, convolution of Y to T. Why are these two expressions equal? Earlier we said that for real numbers we didn't need that complex conjugate. So I'm going to try to explain. I have my nice little 3D prop here of a real space sinusoid. Alright, so if we look at this from the end, we can see the twisting, and this is what is represented by the e to the negative j omega t. And so in this space we would cut it in two different dimensions. So we would cut one dimension this way, and that would be our imaginary. And we cut another way this way, and that's the real. So if we want to look at just the imaginary, if we lay it down like this, we can see how it goes up and back. This is what we see projected from that 3D spiral onto the imaginary plane. So I'm going to just try to trace it on this paper so we can see that it goes down, and I'm doing a terrible job of tracing. Yeah, you get the general idea. Okay, so we can see if we project this down onto the sheet of paper, and if this is the imaginary plane, the piece of paper is the imaginary plane, that would mean that the real plane is standing up behind it, and this projection this way would be the real. And so there would be a sinusoid going up and down, and that's the real part of this signal. So now what we did when we solved out this relation between the correlation and the conjugate, we said we need to do a time flip, and this was derived for real values. So let's see what happens when we take this, and if time is here, we're going to flip this axis around. We're going to just take this and say that t is equal to 0 is right here, so I'm going to put my finger there and hold it, and we're going to flip this around this way. And what we see, I don't have enough room on my table, I'm running into things. What we see is we turn this around, and so t is 0 is here, and then I'm going to move this back over here. What we see is that this one has not been flipped. It has been flipped, but it's also been inverted, because the sinusoid was inverted in the time flip. So a flip along the time axis results in an inverse on the imaginary axis. Does that make sense? So originally we were going down, then up, then down, and when we flip it around, and now we're looking at it, we would continue this on. Now it's going to start to go up, and then down, and then up. So if you can think about that, if this projection, if the palm of my hand is the real axis, and so we're flipping that in time, what that does in the imaginary axis is it actually does an inversion on the flip. So that's why we have to do the complex conjugate, is to then, once we rotate this around, okay, now up is down and down is up. So we do the complex conjugate to now take this thing and flip it over. And when that flip is done, then this peak is now facing down, which is where it's supposed to be. So the complex conjugate is needed in this equation if we're working with complex numbers. So when a rotation or a flip in time, that actually causes an inversion in the imaginary space. I hope that is a good enough explanation. I'm not going to go into the mathematical derivation. We've talked about some of these things before, and we're engineers, so if we can conceptualize it, that's good enough for me. There are mathematical proofs, and I'm sure that we can find them out there. Alright, I'm going to set this back down real quick. Sorry for shaking the world around. I don't do much video editing, so this is probably going to be a really shaky video at that point in time. Alright, so now we can return to our example. So this was just a little aside note about what is a complex conjugate. So now let's go back to our example. And we're going to look at how we use this information to obtain something useful. Alright, so back to our example. We have y of t is equal to lambda divided by r squared times x of t minus t naught. X of t is composed of two parts, the cyclic prefix and the data that's going to be running in this repeating pattern where we have, cyclic prefix data, cyclic prefix data, cyclic prefix data. Okay? So now we need to sorry. Okay, so we talked about that. So, where does this leave us? Okay, I finally found my place in my notes. So, what we want to do, we want to now find the output of the matched filter. So we're going to modify our system a little bit. So what we had before, we had the transmitter, T of x, fixed in space, transmitting. This is going to transmit the value of x of t. This is going to be received on the receiver side. This is y of t at the Rx node. And then this guy, he's going to now feed in to what we're just going to call our system. And for this example, we're going to go ahead and call it H. And H is going to encompass what we talked about earlier about the 802.11 system, but just of the signal detection. And so if we rewrite this, we actually have two systems now. So we have x of t that's feeding into H1, and let's go ahead and call this H2. H1, this is outputting y of t that's now going to be, the output of H1 is going to be the input of H2. And H2, let's just call it Z. Z of t. Okay, so now we've got two systems that it's going through. This first system, H1, is described by the following equation. H1 is described by y of t is equal to lambda divided by r squared times t of t minus t naught. Now what we want to do is find a system H2 that's going to result in these peaks. We're going to do that with correlation. But we don't actually want to implement correlation. Convolution is much easier to implement in a true system. So we want to massage this to get it in the form of a convolution. So we take our S of t with our star notation, y of t, and we know that in the complex conjugate, negative t, convolution, now of y of t, because this is now going to be the input to H2. So if we do this, this is going to give us our second, this is going to give us Z of t. So H2 is described by the system, or Z of t is equal to S complex conjugate of negative t convolution with y of t. Let's go ahead and throw this into the integral format. We're going to say this is equal to the integral from negative infinity to infinity of x, for this one, we're going to use y of t, and then I'm going to say h of k of t minus tau, t tau, where h of, and let's actually call this, h of k is fine. Sorry, I'm mixing all types of notation. H of k of t is going to be equal to s complex conjugate of negative t. Alright. This is the matched filter equation. And this is very important. So this is the matched filter. So the matched filter is equal to let's just go like this. All of this is the matched filter. So the important thing to remember, matched filter, time flip, complex conjugate is what we're using for our filter coefficients. So let's take this one step further. What do we have? What do we have for these matched filter coefficients? The next thing that we're going to talk about is a Barker code. Barker code. A Barker code is a special code that correlates with very low side lobes. So in the last class, if you remember back, we were talking about the correlation of a sinusoid. And we saw that when a sinusoid correlated, it had this little loop here, and then it went down, and then it went up a little higher, and then it went down, and then it went all the way up, had a high correlation, and then it went down and up, down and up and down, something like that. Is that right? Double checking my notes. Did I get the right number of bumps? No. Well, yeah, it depends on how many cycles of the sinusoid you consider into it. And these will keep going down if you have a sinusoid that is turned on and off by a rect function. So this would actually have, you can count the number of peaks, and this is the number of peaks in the sinusoid that integrate up to form lobes. So when we're looking at side lobes, this is the main lobe, and this is the side lobe. Usually, the side lobe that is right next to the main lobe is going to be the highest. So stating that there's going to be correlation right next to after it nulls out. So this is the thing that we're trying to minimize. And depending on the type of signal, there's a lot of different minimizations that can go on, or we're trying to maximize this. So a Barker code maximizes this. Okay, the specific one that we're going to look at is a Barker 7. So a Barker 7 is defined by, and I'm just going to call this B7. This is defined by 1, 1, 1, negative 1, negative 1, 1, negative 1. So this is the sequence that's transmitted. And if it's transmitted in this order, if you shift these to the side and try to correlate it again, or shift these the other way, however many, they don't correlate unless they're right on top of each other. The longer the Barker code, the better it gets, the more it suppresses the side lobe. And there are books and books and books that contain different types of Barker codes and different special codes that are specifically formed to minimize the side lobes. And this is a very big area of research, and if you can find a longer code that doesn't correlate up, or that meets the Barker code criteria, it is a huge thing, because this is what communication systems use to obtain time sync. Okay. Alright. I've got to bring up a MATLAB example, and so I'll switch to the next video.